All right, good afternoon, everyone. Let's see, where did we stop last class? DC sources from batteries, voltage dividers, yeah, application, and then divider-based DC sources, electronics. Let's switch over to the notebook. And then let's see here, op amps. Okay, any questions regarding applications of resistors as voltage dividers? How about here? As biasing circuits for transistors. Application is different, but the principle is still the same. Okay. Principle is we're trying to obtain a variety of voltages from one single specific source simply by varying the value of these resistances. And then electronics, op amps. You have a voltage divider network right here. Network or circuit, divider circuit. And then, of course, in a 10:1 oscilloscope probe. Right near the connector. Okay, the connector is far bigger in size than a standard connector. Okay, voltage summation of two resistors. I believe we had covered this too. So I just want to make sure everybody has, if anybody has any questions before we proceed. Okay. All right. All right. So the voltage weighted summation as applied in electronics. This is something that we will look at in op amps. Okay, op amp based amplifiers. So typically the op amp is drawn like this with an output on the right. You have a resistor going into the inverting terminal, and then the non-inverting terminal is connected to ground, and you have a feedback resistor. This feedback resistor feeds a bit of the output voltage to the inverting terminal, which is V minus. So this is V minus, and this would be V plus. And what this RF and RI do is they create a voltage divider network similar to this. Okay, so R1 and R2 or RI and RF create a voltage divider network. And so a small portion of the output, V out, is fed back into the input. Okay, that portion that is fed back into the input is R1 over R1 plus R2. And we saw that in the previous slide right here. Right, we had this equation. Okay, so the voltage here would be V minus, and that V minus is basically a fraction of V in and a fraction of V out going into the circuit. Again, the application we'll look at later on, but for now, the topic that we are focusing on is that we can use resistors to create different kind of biasing networks, and same principle can be applied in a variety of applications. Okay. All right. Any questions? Okay. All right. In 315, you're going to see an amplifier circuit like this. Okay. When we see an amplifier circuit like this, there's biasing on the output side. And there's this biasing on the input side. And we spoke about this just a few slides ago. There are two resistors, 20K and 3.6K resistors create a voltage divider bias. So voltage divider bias. Okay, so these two resistors create a voltage divider bias, meaning if I was to take the Thevenin equivalent of the circuit simply from the perspective of, actually, there's no need for this. We only need this. Okay, so I have this transistor, I have these terminals. If I was to find the Thevenin equivalent circuit between A and B, you apply 12 volts here at the top, voltage divider, two resistors in series, creates this effect. This is equivalent to this, right? 12 volt source is connected to these two resistors, and I'm taking the output across here. So the Thevenin equivalent to this circuit would be a voltage source in series with a resistance. This voltage source VTH will have a value of 1.83. This is something we already saw previously. So if you're a designer or if you're an engineer trying to understand a system and you look at a circuit like this, you would immediately should recall that if you have a voltage divider network created from two resistors, it should look something like this, where you have a Thevenin equivalent voltage and a Thevenin equivalent resistance. VTH for this particular example was 1.83. We have seen this previously. And RTH, 3 kilo ohms, two resistors in parallel. And so that's how the circuit looks going into the transistor. Okay, so into the transistor, it looks like this. This is an immediate application of a Thevenin or Thevenin equivalent circuit. Okay, oftentimes the question does come up, we are doing this and we keep saying that it's important. How and why is it important? Well, Thevenin equivalent network is part of the analysis of larger circuits. All right, let's take a pause. Think over that. Let me know if you have any questions. Any questions from anyone? Okay. All right, R to R ladder networks. R to R is the ladder network is basically, as you can see, the shape, right? It's a ladder that's laid down flat on its side. Okay. But this is known as a ladder network because there are steps in there. And depending on the direction of the voltage or current, we're either seeing the step up or step down. So let's look at this circuit first from the far right. We have a circuit that is comprised of 8 resistors, and there's a group of resistors with the value R, meaning they're all the same in value. And there's another group of resistors which is twice, which is 2R. If you look at the far right, you will see 2 resistors in parallel. Okay, 2 resistors in parallel. Now, this kind of circuit, when you have 2 resistors in parallel on the far right, if you draw out the equivalent circuit, I'm just going to draw out 1, 2, 3. Okay. this resistor is 2R in parallel with 2R. So what is the total equivalent resistance of those two resistors? Don't need a calculator or anything for that. Yes, it's just R. Sidebar, a quick, I don't know if I've mentioned this in class, but I'm mentioning this here. A quick way to calculate is if you have, actually, you know what, let me pull this down and then. For N resistors in parallel, all with a single same value called R, the total Req is R divided by N. Doesn't matter how many you have in parallel. Okay. If you have N resistors in parallel, you have two resistors in parallel, 10 ohms each, Req is 5. If you have 10 resistors in parallel, all with value of 10, Req is 1. It's simply the resistance divided by the number of resistors. That's it. So 2R and 2R in parallel gives us an equivalent resistance of R. Then that R is in series with this resistor at the top. This would be a series connection. And so this would be equal to R plus R gives me 2R. And that again brings it in parallel with the next branch. And so on and so forth. It continues from right to left. We start off with two resistors in parallel that reduces to R. That R is in series with this R, gives us 2R. That will be in parallel with this one, which is 2R. So again, we get R as an equivalent, which in series with this one gives us again 2R. In parallel with this gives us again 2R in parallel with 2R, R, and finally we have R over here. So Req, looking into all of these circuits, 2R, 2R, 2R. And the reason is because you have two resistors in parallel on the right. So it gives us R plus R gives us 2R. Okay, that's what those arrows mean at the top. Looking into the circuit from that point. Okay, let's take a pause and let me know if you have any questions. Have you seen this circuit before? Okay. Any questions? All right. So then let's see what happens for the current. So for the current, we're going to start from the left. From the left, let's say, and this is solely due to the fact that we have 8 total resistors. Okay. Because you have 8 total resistors, we are just starting with an equal value, let's say 16 times I. Right? At this point, we don't care what that value is. But let's say it's 16 times I because we know it is going to be divided into 16 parts. Okay. And so that's why we're starting with 16I. If we start with 16I, splits into exactly 2 equal parts because both resistances are 2R and 2R. Okay, 2R and 2R. And so it splits exactly into 2 equal parts. is 8I and 8I. Okay. So 8I goes down, 8I goes towards the right. And that 8I goes towards the right, it splits into further two parts. Again, because the resistances are equal on the right, 2R and 2R. And so it again splits in half, and you get 4I and 4I. When it hits the next node, it again splits into two parts, 2I and 2I. And finally, we have two resistors in parallel. And so this 2I splits into two equal parts, called as I and I. Okay. Doesn't matter what the actual value is. We're just simply stating that it's 16 times it because it divides across 8 different resistors. Okay, so it's dividing 4 different times. Okay, it's dividing into 4 different ones. All right, let's take a pause, go through it. Let me know if you have any questions. Does everybody understand how this circuit works? Okay. Now, obvious question would be, again, where would we actually use this kind of circuit? The answer is right there at the bottom. This kind of resistive structure is again used for biasing and current limiting, specifically for digital electronic circuits, and where we want to create a digital to analog converter. This is not something that you look at now. It's later on in 315, but these kind of resistive ladder circuits are used for those kind of digital circuits as biasing resistors. All right. You've already worked with LEDs in the lab before, right? Okay. So energizing diodes from voltage sources and batteries. A typical red LED, gallium arsenide with a little bit of doping, requires about 1.9 volts to start conducting. Okay. LED is just light emitting diode. Diode has a symbol that is a triangle, a small triangle in a line running across. It has two terminals, A for anode and K for cathode. The name diode comes from the fact that it has two terminals, but it actually derives its name from its vacuum tube diodes. Okay, so early days of electronics, we had vacuum tubes as electronic devices. Vacuum tubes had two electrodes, one positive, one negative. Positive was the anode, the other one was the cathode. Diode simply means two electrodes. It's the name carried over, and hence a solid state device, which is the one-way device like this, is known as a diode. Current only flows, so a diode voltage is always measured with positive reference at the anode and negative at the cathode. Current always flows in this direction. Plus to minus. A diode is a one-way device. If anode is more positive than the cathode, then the diode is said to be in the forward mode. If the anode is lower than the cathode in terms of voltage, then it's in the reverse mode. So it's forward bias and reverse bias. It only works in forward bias, does not work in reverse bias. Details will be studied in 315, how and why that is. But in 115, we are taking diodes and we're using them in circuits for applications. Okay, so in this example, if you have an LED, the LED typically turns on at 1.9 volts and requires current of 20 milliamps. So if you take, in real life, I was just saying, if you take an LED and you take one of those coin cells, you know, the small ones, everyone know what I'm talking about? That goes into your alarm key fobs and small places, small flashlights. You have small button cells or coin cells. You can take an LED and you can put it across. So those coin cells are like cylinders. And so you can take the LED and you can just put it across this, the two terminals of the battery, and just turn on. And one of the reasons is because those are low current batteries. Okay, they have a limited amount of energy, small space, small size, cannot supply more. So you won't end up damaging your LEDs. Okay, you can create a small flashlight with just one single LED and one single button cell. And you can try it out for yourself. If you have a coin cell lying around somewhere, you have LEDs in your lab kits, you can do so. Okay, but let's say you have these kind of batteries, AA batteries with 1.5 volts each. So these are AA batteries, plus minus, plus minus. It's 1.5 volts, 1.5 volts. You connected them in series. So total voltage is now 3 volts. But if it's 3 volts and it's large, this large of a battery, you connect it directly to an LED, it's going to burn very bright. It's going to turn on very bright. And there's also going to be a large amount of current flowing through. Okay. So LED might, well, burn out very quickly. And we don't want to do that. So what do? We put a resistor in series with that LED. Okay, we put a resistor in series with that LED. And what the resistor will do is it will limit the current and drop some voltage across it. And so these resistors are known as current limiting resistors. All resistors, by the way, can be described as current limiting resistors. That is the primary function of a resistor. It's a very simple yet fundamental device. We cannot build any circuit without a resistor. I probably have mentioned this before, but I'm mentioning it again. Okay, we cannot build any kind of electric circuit without a resistor. Resistors are a must to control the amount of current that flows through our circuits. Okay, so let's take a pause. You think over this, and let me know if you have any questions. Any questions? Yes. So question being asked is, resistor will only create a voltage drop. How does it limit the current? So we'll just use Ohm's law in mathematical terms. If we apply Ohm's law and KVL, if you apply KVL around this loop, what do we get? If you apply KVL, we have 3 volts, and 3 volts is dropped across the LED plus the resistor. So we have VR plus VLED, right? You're applying 3 volts, energy supplied must equal the energy received. And VLED is 1.9 given to us from the specs. So the voltage drop must equal 3 minus 1.9, which is 1.1 volt. So the resistor must drop 1.1 volt across it. Now, the second part of this is that the LED requires only 20 milliamps of current. Okay, 20 milliamps of current. We should not exceed 20 milliamps of current. That's the given spec. So at the beginning of the design, we are given that the LED requires 1.9 volts and maximum of 20 milliamps. All right. So now if you look at the circuit, what do we see? The resistor and the diode are in series, which means that the current through both of them is the same. So if 20 milliamps is going through the LED, 20 milliamps must go through the resistor. And now we apply Ohm's law. We know VR should be 1.1 volts. Actually, VR is I times R. I have VR as 1.1 volts. I have R as 0.02, which gives me a resistor value of 55 ohms. So when current passes through, the resistor is opposing the flow of electrons. So it's dropping some voltage across it. And then we are designing a circuit from the spec of the LED. Does that answer your question? Okay. Again, this is, yes, go ahead. Yes, that is correct. So question being asked is, what am I using in the equation? Are you talking about this one or are you talking about this one? The Ohm's law. Yeah, so those specs are obtained from here. So these are the given specs. .9 volts at 20 milliamps. And so the maximum current, excuse me, the maximum current that I want in my circuit should not exceed 20 milliamps. If we said we could go up to 30 or we could go no more than 10, we would simply take this value and change it out. So this value here is my current limit. Conversely, if I change the resistor value, then my current will decrease, right? Right now, my resistor is 55 ohms. If I use a resistor of 50 ohms, let's say, or 47 ohms, let's say, right? If I use a resistor of 47 ohms, my resistance drops. That means my current would increase a little bit. So my current, instead of being 20 milliamps, might be, I don't know, 21, 22 milliamps. Slightly larger, not enough to damage the LED. The LED will still work. It doesn't, yeah, nothing will happen to it, but it's larger. How many LEDs do you have in your lab kits? Just one? Are you all done with all the LED experiments, or is still more to come? Just one color LED? LEDs are cheap. I mean, I have like 3 cups full of LEDs on my desk. So next time you're in the lab, if you want to burn one out, just hook it up to like a resistor and crank up the voltage to like 5, 6, 7, 8 volts. See how bright it gets. If you want to do a simple experiment, you can measure the current that's flowing through. If you burn it out, I'll give you one. Fine. You can have your pick of colors. I have red, blue, green, yellow, tricolor LEDs. There are LEDs which are like transparent, have 4 leads coming out. You can do RGB in there. And you do turn all 3 of them at the same time, you get white light. RGB, 3 colors. So it's a lot of cool stuff in electronics. Okay, coming back to this example. This is also, this is the fundamental operating principle of a flashlight or a system designed for a flashlight. Okay, all flashlights are this. You just have a battery and you're connecting a light bulb to it, and that's it. That's also one of the first circuits I ever built as a kid. I had like a battery and I put like a small, flashlight light bulb across with the 2 wires. But here's the difference. LEDs are electronic devices, so they need the current to be limited. Whereas when you have a light bulb, the light bulb itself has some resistance. Okay, so you don't need a resistor. As long as the light bulb is within the voltage spec of the, of your energy source, which in this case is 3 volts, you can simply take a 3-volt battery or a 1.5-volt battery and connect it directly to like a regular light bulb, like a filament light bulb, not an LED, like a filament light bulb. Okay, I still have like old flashlights somewhere in my toolbox that have like old filament light bulbs. And so those are the same incandescent light bulbs that we used to have everywhere. And you take that, you connect it across a 1.5-volt battery like this one, and it'll just, turn on. And you put a switch in there, you got yourself a flashlight. That's what it is, right? So again, there are some interesting projects that you can do on your own. As I said, you can buy like a coin battery for like a couple of bucks. You can buy like 1 or 2 of those. You take the LED that you have, and you stick it across the coin cell battery, and as soon as the terminals touch, it's gonna light up. That's a flashlight, mobile flashlight. Okay, let's see. Where's the mouse cursor? There you go. All right, ignore this. It's not Friday or anything, but I left the slide on here just to give you an idea of what could be on the final exam. Okay. So in case you're wondering, there is no midterm in this class. We are doing a series of quizzes, but on the final exam, there could be problem about superposition. So superposition. Problems that have 2 or more interrelated tasks, maybe not. I'm kind of like 50-50 about it. You will know about this. Definitely, you'll have an answer for this in the final week. I won't leave you hanging. I will let you know whether it's going to be on there or not, right? Reverse engineering problems, most likely not. So I would say, let's scratch that one out for now. Okay. Okay. And problems that test basic skills, definitely 100%. 100% yes. Okay. Some of them could be plug and chug, or I like to say plug and solve. So I would say could be plug and solve, meaning you have an equation, but you need to figure out what the system or the problem is asking you. And once you figure out the equation, all you have to do is you plug the values in there and you solve it. Okay, straightforward. So there's no in those kind of problems, there's still some value in those kind of problems. Okay, I still see some value in there. The value is that this is not about developing your problem solving skills, but it's actually about understanding what the problem is asking. Okay, so it's a straightforward equation, but if you understand what it's asking and you determine that this is the right equation to use, then you simply plug in the value. So there's still some value in those kind of problems. There's a learning value in those kind of problems. And this one, definitely. So there will be circuits where connections are neither in series nor in parallel. And that is true of most real life circuits. Okay. And so you'll see circuits like those two. Now, it's not as if it's going to be like a separate problem for everything. Okay. There could be like 1 or 2 problems that cover like 2 or 3 of these points all at once. And again, as we get closer to the final exam or the finals week, that's when we'll refine this list and you will know exactly that's going to be asked, or the topics that are going to be asked in the final exam. Yes. So it's the quizzes altogether comprise 35 to 40%, probably a little bit more. In the final exam will be maybe about 25, 30% is, I want to say. Yeah. Having a midterm in there just puts a big chunk of the grade is then devoted to the midterm, which I don't like to do it that way. When we get to semesters, even the final exam is like, we are still devoting a big chunk, but with the quarter system, it's just not possible to have like 3 or 4 big assessments. So my personal preference always is to split it up into multiple parts rather than have like one big chunk. So if somebody is having a bad day and doesn't do well on that big assessment, it should not affect their grades disproportionately. That's kind of my philosophy about it. Okay, let's see. That should be the last slide on this one. There should be the next one. Let's see. Oh, need to. Okay, so the next topic here is linear and parametric circuits. Sorry, non-linear and parametric circuits. Okay. So far, we looked at resistors. Resistors are the most fundamental of devices. They are linear devices. Yes, called linear because the voltage and current for a resistor have a linear relationship. Okay, Ohm's law, V equals IR. V is directly proportional to I. If V or I increase or decrease, then the other quantity must increase or decrease correspondingly, right? Both go up at the same time, both go down at the same time. Constant of proportionality is the resistance value R. Now, non-linear devices. So this is, of course, linear resistive networks. You have resistors plus your sources. That's what we looked at. And then we have non-linear devices. And the most fundamental of those are diodes. Diodes also come under the purview of semiconductor electronics. Okay, semiconductor electronics. It's a one-way device. It's a one-way device, conducts current only in one direction. In the other direction, it is off. So in one direction, it's on. In the other direction, it's considered to be off. Okay, so those are the nonlinear devices. So from diodes, which is the fundamental two-terminal semiconductor device, we have transistors, which are three-terminal devices. Then there are something known as SCRs and triacs, which are four-terminal devices. There are, four terminals and four material sandwich structures. Okay, that's not something we study in here. So again, diodes are two-terminal devices, but they are non-linear because the current and voltage for a diode do not have a linear relationship. Okay, current and voltage for a diode do not have a linear relationship. If we plot we introduced VD and ID. So if we plot diode current as a function of diode voltage, the characteristic looks something like this. Okay, so it's non-linear over its entire portion. There are some linear portions, meaning once it turns on, right here, after it turns on, this is known as the turn on voltage. Until and unless this voltage is applied to the diode, you would not see any current flowing through. But once it goes past the turn on voltage, then the current increases rapidly. Okay, and in that specific portion, we can state that it might be linear, but that's a different thing. Overall, the device is non-linear. Okay, and so you've already used this in the lab. We've looked at some introductory circuits using diodes, and then we'll look at more diode analysis in this under this lecture. So one thing about the techniques that we learned about superposition. Superposition applies only to linear circuits. If it's non-linear, we cannot add them directly. It only applies to linear circuits. And if you have a circuit as shown here, if you have a circuit with linear resistors and nonlinear diodes, you can still separate them out and apply superposition and Thevenin and Norton techniques to the linear portion of that circuit. Okay, we can still apply it to the linear portion of that circuit. So I think on this slide, in the previous slide, stay the same thing, can be applied only, sorry, on this one, we apply linear portion of the circuit or the whole circuit because it's linear resistive networks. In nonlinear circuits, we can only apply it to the linear portion. Okay, so we can isolate the linear portion right here, and we can apply all those techniques. All right, the diode itself has its own equation that relates the diode voltage and diode current. Okay. You have, in the lab, you have used photodiodes as well as IR diodes, right? Infrared LEDs. So let me talk about the symbols a little bit. If you, how I talked about this before in 115, arrows coming out and arrows coming in. Okay. If arrows are coming into the symbol of the diode, it means it's a photodiode, solar cell. And if arrows are coming out, then it's emitting light, right? So light emitting diode. So these are light emitting diodes, LEDs. Infrared LEDs are also light emitting diodes because they're emitting infrared light. All right, parametric circuits. The definition of parametric circuits is that the action of the device changes in response to a control parameter. Okay, so there is a control parameter in the circuit, and the response changes based on the control. Okay, and so those are parametric devices, parametric circuits. So there are sources that are dependent on some other quantity. Okay, those are known as dependent sources. They are symbolized by this diamond shape. Okay, this is the symbol for a dependent source. The circle indicates it's an independent. So far we have only looked at independent sources, only circles. There are some circuits that can have dependent sources. Dependent sources can be both. You can have a voltage source, you can have a current source, and you can have, based on the control, you can have a controlled voltage source or a controlled current source. And the dependency could be on both voltage and current. So it's a 2x2 cross matrix. So you can have a voltage controlled voltage source or a voltage controlled current source. Okay. And in that case, it would mean that the source, whether it's voltage or current as the output, is controlled by a voltage in some other part of the system. All right. So there's a voltage. Let's say we have a circuit and there's a voltage in one part of that circuit, and that voltage controls the output voltage or current in a different part of the circuit. And so that different part of the circuit can be considered to be as a dependent source because it is supplying a rated voltage or current, but it's controlled by something else. And similarly, you could have a current controlled voltage source or current controlled current source. So there we have these four definitions right there. Okay. We still have a couple of minutes. For the most part, these kind of dependent sources are used in models. Specifically, we have the transistor that you'll learn about in 315. The op amp can also be said to have a dependent voltage source at the output, okay? Because the output is dependent on some other part of the circuit. But let's talk about an immediate example that we just saw in the last few lectures. We have the voltage divider network, right? We have the voltage divider network. In that example, I had 9 resistors and I had 9 volts connected to those 9 resistors in series. So I had like every resistor had 1 volt, 1 volt, 1 volt across it, right? So every output across every resistor can be considered as a dependent voltage source. They're all supplying a certain voltage, but that output depends on the input. If my input goes from 9 to 18, what happens to the output of the resistors? It's going to double, right? Voltage divider network. You're applying a input voltage and you have this voltage divider network and these output voltages coming out. And these output voltages can be considered to be a dependent source because they're supplying a voltage, but they depend on a voltage that's in a different part of the circuit. In this case, the input. If I change the 9 volts to like 10 volts, then the corresponding output is going to change. If I change from 9 to 18 to 27 to 54, correspondingly, the output voltage across the resistors will also keep going up. Does that make sense? And so we can theoretically model that as a dependent voltage source. In this case, it would be a voltage controlled voltage source. Okay, it'd be a voltage controlled voltage source. So a resistive voltage divider network can be said to be a voltage controlled voltage source. All right. And there are some other models, again, we said, we can look at in 315, but this is something fundamental that students should be aware of in 115. Okay. All right, we'll end class here today, and I will see you all on Friday.